Given an M by N matrix board, each cell is capital X or capital O. Example 1 is 4 by 4. The bottom row has a single O on the edge at column 1, it touches the border, so it stays O. The other 3 O cells sit in the interior and cannot reach that border O through only up, down, left, right moves past X walls, so they are captured and flipped to X. The result keeps that one border O. In this game, the edges are escape hatches. Any O sitting on the border is automatically safe. And because safety is contagious, any O connected to an edge O is also safe. Instead of hunting for trapped cells, we're going to act like a flood. We'll start at the borders and let safety flow inward to every connected O. Anything the flood can't reach must be trapped. When we find a safe O, we temporarily rename it, let's call it T. We do this for every O on the border and use DFS or BFS to tag all their neighbors. By the time we're done, the board is a mix of X, T, safe, and O, trapped. The final step is the cleanup. We walk through the entire grid one last time. If we see a plain O, it means the flood never reached it, it's trapped. We flip it to an X. If we see a T, we change it back to an O because it was safe all along. Whether we use a recursive dive or a spreading ripple, the result is the same. We only trigger the search from the border cells. This keeps our work efficient, ensuring we only touch the cells that actually have a chance of survival. We start by patrolling the perimeter. Any O on the very edge is an escape hatch. We mark each such cell with a hash sign for safe, and push it into a queue so it can unlock its neighbors. Breadth first search expands from those border seeds. We dequeue the front cell, inspect its 4 neighbors, and whenever a neighbor is still a plain capital O we mark it safe with a hash and then queue it. Cells at the same shortest hop distance from the border are discovered in the same wave, we keep dequeuing until the queue is empty. Layer 0, the queue still holds the bottom seeds, each already rewritten as a hash. We pop them in order. Whenever a neighbor is still capital O, we mark it with a hash and append it so the next layer can process it. Layer 1, the frontier sits on the 3rd row from the bottom. Again we pop, scan 4 neighbors, hash every plain O, and push it on the queue. The solid X row above acts like a dam, so the flood never reaches the pocket on the top half of the board. Once a cell is marked safe with a hash, we never enqueue it again. That way each coordinate is handled at most once, so the search stays finite and efficient. Finally we sweep the whole grid. Any plain O was never reached by the wave, so we capture it to X. Every hash was safe, so we restore it to O. The board now matches the capture rule. Time is order M times N, we scan the border, each cell is enqueued at most once in the BFS, and we do one final pass over the grid. Space is order M times N for the queue in the worst case when a large region of O cells connects to the border. Entry point, modify the board in place to capture surrounded regions. Let M and N be the grid height and width. Use a FIFO queue holding row-column pairs for breadth first search. Outer loop walks every row index R. Inner loop walks every column index C. If this cell lies on the outer border and still shows capital O, it is a seed for the flood. Enqueue that cell and relabel it with a hash so we never enqueue it twice. Drain the queue until every reachable O from the border is marked. Pop the front cell as the current flood position. Consider its 4 neighbors up, down, left, and right. If the neighbor is inside the grid and is still plain O, it inherits safety from the flood. Mark it with a hash and push it on the queue to continue the wave. Second double loop scans the whole board for the final rewrite. Inner loop over C finishes one row before R advances. Any O left was never reached, so capture it by writing capital X. Any hash was temporarily safe, so restore it to capital O.